So far we have been looking at propositional logic. Propositional logic is a logic of sentences, and essentially if you are given a certain set of sentences and told that they are true, then you can explore the logical connections between those sentences and also determine which other sentences are true essentially. But we find that this logic is not expressive enough, and that is the reason we want to move on to this first order logic, which is the most popular form of logic that is used, because it is quite expressive. We can say a lot of things in first order logic, and yet it is within reasonable amounts of computational complexity. So, we begin looking at first order logic. So, we will use the notation FOL, but we also sometimes call it predicate logic, because it uses a notion of predicates which I am sure you are familiar with, also called predicate calculus. For example, we said propositional logic was propositional calculus. So, these are terms that we will use interchangeably, but we will use the term FOL most of the time essentially. Why are we interested in this? Because if you remember, we started with the Socratic argument, when we said that what do we mean by logical inference, what do we mean by deduction. Essentially we said that if you are given a sentence like all men are mortal, and if you are given another sentence which says that Socrates is a man, then we should be able to infer that Socrates is mortal. This form of reasoning we said was the syllogism, one of the 16 or 19 I do not remember syllogisms which the Greeks had specified. Now, the trouble is that if we try to encode this in propositional logic, we cannot really say very much. So, we could say for example, that this is P and this is Q and this is R that we want to show, and there is no connection between them that we can see, because in propositional logic we accept the sentence as an atomic unit. We cannot look inside a sentence and say what is this sentence talking about essentially. So, in fact, the fact that sentence is talking about men and men being mortal and Socrates being a man is hidden from us, because at the sentential logic level we just treat the whole thing as an atomic unit essentially. And at that point we had also mentioned that in the first order logic what you would end up writing is in the language something like this. So, our given statements would have been these two statements. The first statement is essentially a rendering of the same English sentence all men are mortal in first order logic, and the second sentence is likewise the second sentence in that which is Socrates is a man, and from this we would want to derive the sentence that mortal and as we will see, it is indeed possible to do that in first order logic. We will be able to derive. So, what does it mean by derive? By derive we mean that just use a syntactic procedure which does only pattern matching, and you are allowed to add new formulas based on certain rules of inference, and then you can add the formula that you are interested in essentially. We will see that it is indeed possible to derive mortal Socrates, but before we do that we need to sort of define our language, and in this case we will see that we also need to define, we can also define what do we mean by sentences in our logic. So, we can define the semantics more explicitly. In propositional logic, the semantics simply say that P stands for certain some statement, Q stands for certain some statements, and if we have a sentence of the kind P implies Q, and if we have P, then we can infer Q. The modus ponens rules will still carry over to first order logic, but here now we will also be able to talk about the meaning of sentences essentially. So, we begin with syntax as usual. And as we did in propositional logic, we will see that the FOL alphabet is basically an augmentation of the propositional logic augmentation. We will add certain more symbols and we will be able to write more, in some sense, complex sentences essentially. So, we start with the alphabet as usual. So, we have the logical connectives which we had in propositional logic, and as in propositional logic we can choose which connectives we want to work with. So, these are some of the connectives that we would be interested in, and we will also carry forward the brackets that we use basically to break up compound formulas into simpler formulas. And we will also carry forward the two constants that we had in propositional logic. So, these were kind of constant sentences, and the first sentence which we read as bottom stands for something which is always false, and the second sentence which we read as top stands for something which is always true essentially. But in addition to that, in first order logic we have a greater alphabet. So, we have a set of variables. So, these are not propositional variables, these are just simply set of variables, which we will call as a set V, and which would be made up of a set of variables. Typically, we use things like x, y, z and so on, or we may use x 1, x 2 and so on essentially. So, if you remember in the last example we said for all x, man x and so on. So, that x was a variable in that essentially. Then we have two new symbols which are this and this. So, the way we will read this is, the first one we will read as there exists, and the second one we will read as for all, which is what we did when we talked about all men are mortal. We said for all x something something something. And then we may or may not include the symbol which is equality. So, if we include it, then we call it FOL with equality, and if we do not, then we have a slightly smaller version of FOL essentially. So, people tend to distinguish between the two languages with equality and without equality essentially, because equality is has certain properties that we can exploit essentially. So, all this was the logical part. And by the logical part we mean which is independent of any particular logic system or logic language that we are defining essentially. Any logic that we define will have these kind of symbols. Of course, we may have a subset of the connectives that is left to us, but essentially all these symbols would be there in any first order language essentially. And then there is a non logical part, and when we say non logical we also mean domain dependent part essentially. What is it that we are trying to talk about essentially? So, there are three sets of symbols here, set of relation symbols, we will call this set R, and this will typically include symbols like P, Q, R, which are like the proportional variables that we used in propositional logic, but we could use something like P 1, P 2, but we can also use something like words of English language, which are sort of meaningful for us essentially. So, man, mortal, and so on essentially. So, we will tend to think of man as a alphabet here essentially. Instead of saying P 3 or something, I am saying man essentially, because if man is more meaningful to us essentially. Then we have the set of function symbols. So, we will use this for that, and typically we use things like F, G, H, or F 1, F 2, but we could also use something like father or successor or sum, if you are talking about numbers and so on. And finally, we have a set of constant symbols. We will call this set C, and they will be made up of constants, and typically we use the first few characters of the alphabet, which is A, B, C, and so on, but we could use A 1, A 2, and so on, but we could also use something like 0 if you are talking about numbers and so on, or a person, for example, Suresh. Now, both this set of relation symbols and the set of function symbols have an arity associated with them, and we will see that when we define the language, this arity tells you how many other symbols it interacts with or takes in some sense essentially. Some people say that set of constant symbols are essentially a subset of the set of function symbols, where arity is 0 essentially. Anyway, this is just for the sake of knowing, we should know that this is often done, but we will distinguish between function symbols and constant symbols, because we tend to think of constant symbols, as we will see shortly, as elements of a domain essentially, or named elements of a domain. So, that was the alphabet, and then we define a set of terms. So, let us use this notation for the set of terms, and we define it by structural recursion as follows. That, so, remember what did we have? We had a set of variables V, we had a set of relation symbols, we had a set of function symbols, and we had a set of constant symbols, and then we had these other logical connectives, and we had this there exists and for all and equality as well essentially. So, the set of terms T is defined as follows, that if I will just use T as a kind of a meta level variable, belongs to the set of variables, then T belongs to the set of terms. In other words, every variable is a term. Likewise, if T belongs to a set of constant symbols, then T belongs to this set of terms essentially. So, every constant is a term essentially. Then if T 1, T 2, T n belong to terms, or if T 1, T 2 up to T n are terms, and f belongs to the set of function symbols and has arity n. So, sometimes we would write this as f n, where this n subscript denotes the arity of the function symbol. Then the function symbol followed by a bracket followed by the n terms is also a term. Now, notice here that, so we say that these terms are arguments to f essentially, and the number of arguments that it takes is basically defined by the arity of the function essentially. But notice that the arguments are terms in themselves essentially, and which means that they could themselves have been made up of another function symbol with another set of arguments which are terms. So, recursively we can write terms which are more and more compound essentially. So, examples of terms in some language, for example, could be for example, in we are dealing with numbers, you may write something like sum 6 7, where sum is a function of arity 2, it corresponds to the sum that we are used to dealing with in numbers. So, that is a term essentially. I could have also written as sum 6 7, sum 4 3, and that should also be a term essentially. So, the arguments to terms need to be terms, that is the only condition that we have essentially. So, we define a set of terms, or as some people say, the family of terms, that is the building blocks of our language essentially. As we will see in the semantics, the set of terms will correspond to elements of the domain essentially. So, if our domain is going to be the set of natural numbers, for example, then this term which is sum of 6 and 7 will stand for the natural number 13 essentially. Likewise, this term will stand for 13 plus 7, which is 20 essentially. So, every term essentially will stand for something which is an element of the domain. Variables are terms that we do not know what they stand for, and we are sometimes trying to find out. Constants are terms which are fixed essentially, we know that they stand for something. So, individual names, for example, 0 or Suresh or Rakesh, they could be constants in a language essentially. Then we have the set of formulas. So, let us call this set f like this. I just need a different f which should not be confused with the function symbols f. So, let us say this is a set of formulas f, and we see in a similar fashion we define the set of formulas. So, initially we say that these two are formulas, top and bottom are formulas, like in propositional calculus they are something which we call them as sentences. We will shortly define sentences here as well essentially. Then if T 1 and T 2 are terms, then T 1 equal to T 2 belongs to a set of formulas. This is obviously in the case where we have FOL with equality. So, whenever we have FOL with equality, we allow this particular formula in the language essentially. We can add brackets here for clarity, and we generally often simpler to add brackets essentially. Then if T 1, T 2, T n are terms and P is a relation symbol and P has arity n, then P followed by T 1, T 2, T n belong to set F. So, now we are using a relation symbol, which also is known as a predicate symbol, and we can take a predicate symbol of a certain arity provided a certain number of arguments, and we have a formula essentially. So, we said for example, in the example that we discussed, man x or man Socrates, both x and Socrates are terms. Remember, x is a variable, Socrates is a constant, but they are both terms, and when he said man x, then man was a predicate symbol of arity 1, and that formula, that thing became a formula essentially. So, sometimes we associate these with atomic formulas. In the sense that you cannot break them down any further, just like we had proportional variables which was kind of atomic, you could not break it down any further. Atomic formulas are similar in nature, that you cannot break them down any further essentially, as far as the language that we are trying to define. Remember that the language that we are trying to define is going to be a set of sentences essentially. Then there are other kinds of formulas which you can say are compound formulas, which sort of build with the connectives and so on. So, if we say that if P 1, P 2 are formulas, then P 1 and P 2 is a formula, P 1 or P 2 is a formula, P 1 implies P 2 is a formula. Negation, the symbol we are using is different. So, negation of P 1 is a formula, and so on. So, this is like in propositional calculus, that if you are given two formulas, then you can use the logical connectives to construct larger formulas. The same thing carries over here, and the semantics of the logical connectives will be identical, as we will see. Then if there is a formula P which you see, and there is a variable x which set V, then So, if you are given any formula which we call p here, and if you are given any variable x, then we can construct a formula by prefixing this p with the symbol for all and followed by a variable x essentially. And we will read this as for all x p essentially. So, for all x p is true essentially. Notice that p may or may not have x inside, it does not really matter, it is a formula. Any formula you can, so that we use the brackets to define the scope of this for all x, which means that this for all quantifier, these two are known as quantifiers, the existential quantifiers and the universal quantifier, they have a scope and this applies to whatever is inside the bracket essentially. Also, then so the same thing follows, there exists x p tidy it up a bit. So, the two quantifiers that we have for all x and there exists x can be used to construct larger formulas. So, you can take any formula and prefix for all x or for all p, there exists x and you get a new formula essentially. So, in the logic that we are working with, we are using these two quantifiers, but there is no particular restriction that these are the only two kind of quantifiers, whereas people have talked about other kind of quantifiers as well. So, if you look at some basic books on logic, for example, some books would talk about another quantifier which says that there exists a unique x essentially, but anyway we will look at only these two quantifiers essentially. So, we have now defined a set of formulas. The formulas that we have are defined by a set of atomic formulas which says top and bottom are atomic formulas. A term equal to another term is an atomic formula, and then if we take a predicate symbol and supply the appropriate number of terms to that, then we get another atomic formula. Then we can take any formulas and use logical connectives to form larger formulas, and then we can apply the two quantifiers that we have to get more formulas. So, all this defines the set of formulas that we have essentially. Now, let us talk about sentences, which is what we are really interested in. So, what are sentences? Sentences are those things which in principle can be true or false, which can be mapped to true or false. In the next lecture, we will define the semantics of first order logic, but we first need to define what do we mean by a sentence essentially. To do that, we first need to define the notion of free variable. So, we say that a variable x is free in a formula, let us call it some formula p, if x is not in the scope. So, remember we had defined the notion of a scope of a quantifier. So, if x is not in the scope of a quantifier, the occurrence of x is not in the scope of a quantifier, then we say that x is free, and otherwise we say x is bound. So, let me give you an example. So, supposing we have some formula which looks like this: for all x there exists y p x y and for all x q x or r x implies, let us say t x y. So, some random formula I have written essentially. So, we need to identify which occurrences of variables are free and which occurrences of variables are bound. So, remember that if a variable is in the scope of a quantifier, it is bound, otherwise it is free. So, you can see that this for all x, this x is bound by this quantifier here, because it comes in the scope here. Likewise, this is bound by this. So, these are bound. This x is also bound, but it is not bound by this one, but it is indeed bound by this one. So, I will just put a cross on the. So, this x is bound. Likewise, this y is bound, because it comes within the scope of this there exists y. So, this is bound by this quantifier essentially. This x, the last x that we have, is also bound by this, but this last y is free, because the scope of the existential quantifier there exists y that we have extends only up to in fact this one. So, the scope of this y is only up to p x y essentially. So, that is why this last y is free essentially. So, in this way you can basically identify free variables and bound variables, and a sentence of FOL is a formula of FOL without any free variables. So, any formula in which there are no free variables is a sentence of first order logic, and having chosen a set of relation symbols, a set of function symbols, a set of constant symbols, we can now actually define a whole set of sentences essentially. So, that is a language that we have. These are the elements of our language, atomic formulas, compound formulas, quantified formulas. As long as they are formulas which do not have free variables, then that is a set of sentences. So, in the next class we will talk about the semantics of first order logic, and we will see that whenever we devise a first order language, we are essentially talking about some domain essentially, and we are talking about relations in the domain essentially.